Hi, welcome back. In this video, we're going to talk about Introduction to Functions. It is going to be basically an overview of everything functions related that you have done in high school. So we're going to talk about what is a function, domain and range, looking at graphs, identifying whether it's a function or not, and how to evaluate a function. All right, well, let's get right to it. So let's start with what is a function. A function, as we've been talking about sets, right? The past two videos have been about sets. Let's talk about how these two sets are related. So a function is a relationship between two sets. We can call it x and y. Those are the most common names that we use for functions, right? We can call it domain and range, input, output. It's just a relationship between two sets such that every input has a unique output. So every input from here will have a unique output. And it can look something like this. It can look at numbers and it can look like a set. The idea is simply that every value from the left, from the input, from the x set, will have a unique output. No matter what happens, everything from here has a unique outcome in this set. And the relationship could look different, right? It could be y equals mx plus b. The relationship could be y equals ax squared plus bx plus c, or the absolute value of x. There's a lot of different functions that we've spoken about in Algebra 1, Algebra 2, all the different algebras, right? And they're all different kinds of relationships, but for every input, we will have a unique output. So let's look at some examples. So here we have three different representations, right? And the idea is, how do we identify whether this is a function or not? How do we identify whether or not there's a unique, for every input, there's a unique output? So we first look at the inputs. And it seems like every input here is unique. Therefore, the output will automatically be unique. Even though we have two sixes here repeating, one has a unique output and two has a unique output. This is a function. Now, on the right side, notice how here we have three unique inputs and they all have an output. The output is unique to 1, right? So 1 only goes to A. It doesn't go to B as well. It has one unique location. The example that I like to use is light switches, right? You can have multiple light switches in a room in your house, but they will only turn on the light. The light switch turns on the light. That's the unique output, right? This is our output, is the light. The light switch can't also turn on the garage door, right? The light switch can't also do the TV. The light switch will only have a unique output, right? So if you have one light switch, you're hoping that there's only one unique thing that it's going to do. If it starts to do multiple things, then this light switch is unreliable. And then it's not functioning, right? It doesn't function. So when you look at this example, I can think of this as having three different light switches in your house. Maybe they're in your kitchen. You can have three different light switches in a room that turn on the same light. That's acceptable, right? Here we have two light switches that turn on the same light. And a different light switch turns on a different light. The problem happens here when you have a light switch doing two different things. Notice how this one does not have a unique output. It has two outputs versus one unique one. And that's when it's not a function. So here we have different function representations. Let's look at the table. Notice how we have two inputs that have the value of 1. But sometimes 1 gives me 2, and sometimes 1 gives me 4. It's unreliable. It has to be consistent in what it gives me as an output. This is not unique. So not a function. We can also look at functions in terms of graphs, right? We might have seen functions in terms of graphs. How do we identify whether or not we have a unique output? Well, we do have this thing called the vertical line test. The vertical line test helps us identify whether for every input we have a unique output. And I can use my pencil or my pen as an example. And as I move it over, as I scan it to the right side, when I cover the input to be 9, right, there's only one unique output, which is right here. And I can move this around. What is the input at 5? We have a unique one. At 10, well, there's only one output. At 12, there's only one output. This is a function. Let's look at here. At -2, there's only one output. Right here. At 0, at 1. Notice how my pencil will only cross the line at one location. Hence, a function. But then what happens here with the circle? Now, at -2, I have two outputs. At -2, it crosses the pencil here and here. And if it crosses it twice, it negates the vertical line test, which means it is no longer a function. Now, you might remember the equation of a circle as x squared plus y squared equals r squared. Just because we have an equation does not mean that it will be a function. The equation will tell me that at -2 we will have this output and this output. But the equation is not a function, and the way to notice is when you look at this function, you can look at this right here. As I solve for this equation, I'm going to end up getting two different outputs for the y value. Now there's a little bit more math that I can show you here, but suffice to say that y squared will result in 1 up here and 1 down here for every single location, except for 3 and -3, right? But we have every value has 1 on top, 1 on the bottom, top, bottom. We have two outputs for every input, and therefore, since it's not unique, it is not a function. Now, once we identify different relationships as unique or not unique, right, we can now look at these functions and talk about their sets, the domain and the range. Now, domain is really just the set of inputs and how it's relating to the set of outputs. The relationship between these two sets creates this as an outcome. So how do I identify which x values resulted from here and which y values resulted from here? Right? We can look at input, we can look at output, we can look at y, x and y. You might have heard of Dixon-Roy, right? Domain input x, range output y. You might have heard as independent, dependent variables. There's a lot of ways of looking at that. But to define the domain, we are looking for the x values, the x in here. So I'm going to look at the x values in my function. And I notice that my function exists only for the x values for everything between -4 and -1. This is my set notation, right? X exists between -4 and -1. Now at -4, we have an open circle, so we just put less than, we don't put the equal symbol. And at 1, we have a closed circle, which means we have a less than or equal to. The alternative is saying parentheses from -4 to -1 with the closed bracket. And we can go back into the notation from set and interval notation in my previous video if you want to look at more of how to write these notations. Now this is the domain. The range is the y values. So the y values are going to exist between what values? The y is going to exist between -7 and +2. right? This is my y-axis. So I'm going to look at vertically, what are the sets, the values in that set? And it's going to be everything from -7 all the way to +2. Now notice how at -7 we have an open circle, so we just put a less than. And at +2 we have a closed circle. The highest value is a closed circle, so we put a less than or equal to. Similarly, we can see how we can have -7 in parentheses and +2 as a bracket, right? It's always from least value, least to greatest. And then you decide whether it's parentheses, whether it's brackets, based on if that value exists or if it doesn't exist. Here we have a different function. It's kind of like a parabola that got cut off, right? It got cut off there. What is the lowest x value that we have? So when you look in the horizontal direction, I can see that 1 is going to be part of my value, my function, for domain. But on the x-axis, we have an arrow over here, which tells me this graph will continue that way. So the x value will not have a minimum. It'll keep going to the left, which means this function will go all the way to -infinity. How do we write that? Well, our set notation, we can say it goes from -infinity to x all the way to +1, including 1. Right? From -infinity to 1, you can also say x is everything less than 1 as our set notation. Or in interval notation, you can say from -infinity to +1 with a close bracket at 1. These are the domain values. Now the range, we're looking at the y-axis. So the lowest y value, 0. And the highest y value, do we have one? No, because this line will continue to push upward to +infinity. So what's the least value that we have? The smallest is going to be 0, and we have a bracket at 0 because we have a closed dot. That value exists. And then the highest value it's going to go is going to be all the way up to +infinity. And since we can't reach +infinity, we'll put a parentheses. There are several ways of saying that, right? In set notation, we can say it's all the y values, where y is greater than or equal to 0. That goes all the way to +infinity. Or you can say y is between 0 and +infinity. Again, for more practice on set and interval notation, you can look at a previous video. But the idea here is, what do we do when we have an arrow? In the horizontal direction, to the left and to the right, we have an arrow going to the left. And then in the vertical direction, we also have an arrow pointing up. So we're going to be dealing with infinity to the left, which is -infinity, and infinity to the top, which is +infinity. And that's how they play a role. Here with positive, here with negative. All right, let's look at our last topic here. We're going to evaluate functions. As you can see here, this passes my vertical line test. It only crosses once. So I can clearly identify one location. Now you might remember this notation, f of x, very common for a function, which says this equation is a function of x, where x is my input. And the result would be my output. So here, x is my input. What is the function? What is the result of the function when x equals +1? So I go to x equals 1, and I notice that the output, the y value is 0. What is the output when the input is -4? I go to -4, and I see that the function exists up here at +4. That's the output. Right? You can look at that point as 0. Sorry. This point exists as -4, 4. Input, output. Now, what about here? Find the value of x when f of x equals 4. When the output is 4, what do we have as our input? So let's look at the function. The function is 4 here, here, and here. We have 3 occasions where the output is 4. When does x make that happen? Well, at -4, at 0, and at +4. -4, 0, and 4. We have 3 situations when that's true. Now, we can evaluate a function on a graph. We can definitely evaluate the function without a graph. Right? So here we have a function. This is a parabola of some sort. I can graph it, but without the graph, I can also identify what happens to the function when the input is -2. So all I have to do to my function is I can plug in -2 for x. So I have -2 squared plus 3 times -2 plus 5. This will tell me where in the graph that's going to be true. -2 times 2 is 4. 3 times -2 is -6 plus 5. With a little bit of PEMDAS, we can combine things. -2 plus 5 gives me 3. So when the input is -2, the function equals 3. Similarly, we can do that for f of 0. What is the value of the function or the output when the input is 0? So plug in 0 for every input value. We have 0 squared plus 3 times 0 plus 5. A little bit of PEMDAS. We got 0 squared is 0. 3 times 0 is 0 plus 5. 0 plus 0 plus 5 is 5. Now, if I were to graph this, the function would look something like, let me see. I don't know. I have to graph this location, right? I would graph this location. I'd have some sort of function that looks like this. At -2, it equals 3. And at 0, we get 5. This is how we would do it without graphing the function. Plug it in for every input and go from there. How do we go backwards? How would it find the value of x when the function equals a number? Well, depending on the function, you would just set the function equal to that location. So if I want to know, well, when does this parabola equal, when is the output 17? Right? When is the function going to equal 17? So we're now looking for the y value. We would go all the way to 17, and we were trying to figure out what location it is. Now, this parabola will have 2 locations. So when you get to like somewhere up here, 17, you would find that the output has 2 of them. It would be 2 outputs. Algebraically, you would just say 17 equals to whatever function you're dealing with. And then you would just solve this quadratic. You'd have to move this value to the other side, set it equal to 0, and then find the factors, solve for x, or use the quadratic formula, and then that would give you your 2 solutions at the end. But that's for another day, right? The idea here is we can do it graphically and algebraically, no matter the situation. All right, guys, I hope this has helped. If you have any questions, please let me know. And as always, we'll calculate.